Hey everybody, I'm excited to get to tell you about my research today. I work in Jun Ye's group at JILA, and we build strontium optical lattice clocks. So throughout this talk, we will be talking about why you should care about atomic clocks, how you can use atoms to tell time, and why these are some of the best clocks in the world. But we're going to back up first and talk a little bit about how I ended up doing research in this at all. If you told me back in high school that this is what I was going to be doing, I would have been very surprised. I knew I liked math. I knew I liked sciences. I had no idea physics in particular was what I was going to absolutely fall in love with. I actually spent a huge chunk of my time back in high school running track. I was a sprinter hurdler and ended up being recruited to run track D1 in college. And so all in all, I ended up running track competitively for 10 years of my life, which is crazy looking back on it. But in college, I was running 25 plus hours a week and traveling to compete at meets every weekend. And it was a huge chunk of my life that I was sort of balancing with a growing love for physics. And I really appreciate having multiple different things and a life outside of physics that matters a lot to me. So it's nice to get a chance to switch your physics brain off and do something completely different and then come back to it later. But through all of this, I was balancing taking physics classes. Here's a photo of some of my classmates from my first ever physics class that I took kind of as a fluke my first semester of college. And I ended up absolutely being obsessed with this class and ended up realizing that I loved it. But it actually wasn't immediately easy to fit into that sphere. I actually almost dropped this class 2 weeks into it. I actually went up to the professor and was like, I need to drop this class. And he was so supportive. But at the time I hadn't processed this, but I felt kind of out of place in that setting. I was one of the only women in the class. I was one of the only varsity athletes in the class. So my schedule looked a lot different from everybody else's who was doing it. And I feel so lucky looking back on it that I had that really supportive professor in that first physics experience, and also that I ended up making just the most incredible group of friends through this class. So we were here celebrating, we had physics office hours, so we were all there working, but it was also my birthday, and so some of them brought me a cake. We were all just celebrating. And I just bring that up because I feel I don't know, maybe more of us can relate to feeling not immediately at home in physics, and you're definitely not alone if you feel that way. But after taking this class, I realized that I just absolutely loved physics. I loved taking complicated systems and taking them apart and making them make sense and building intuition around what makes them work. And so I started getting involved with research, starting off with a project on numerical modeling for astrophysics. So we were actually looking at data from distant stars and using that to determine if they could have habitable planets orbiting them. And I went from having absolutely no background in this field, no clue what I was doing, to eventually over a couple of years, building out my own data reduction system, really taking ownership of a project. I got to present some of my results at the American Astronomical Society conference, and then ended up writing a first authored paper. And so I found out that I actually really like this whole business of doing research. But I thought maybe numerical modeling wasn't it for me. In fact, I wanted to try experimental research and really get my hands dirty. So I joined a different group my junior year. This was Misha Lukin's group at Harvard. And there I was working with tiny atom-like defects in diamond. So a diamond is usually a regular carbon lattice, but every once in a while you'll get nitrogen or something else stuck in there. And these defects, you can treat them a lot like atoms. You can shine lasers at them. And I found out that I love playing with optics. I love building electronics and getting my hands dirty. And the fact that you can test cool physics ideas on a tabletop. This was also when I decided that I wanted to apply to grad school. I decided that kind of late, but because I had incredible mentors in that lab who really, really supported me and encouraged me in that as well. And so now I'm here at CU. I do work on optical lattice clocks, which we'll get into in just a second, but it's also really important to me that I have a whole life outside of physics. I'm no longer running track. I'm now retired after graduating college, but I have an amazing group of friends who I've met through our cohort. I have the cutest dogs in the entire world, and you cannot convince me otherwise. And so it's, again, really, really nice to still have life and balance outside of doing physics all day. So that was kind of just how I ended up deciding that this was the research I wanted to do and coming here. Does anybody have questions about this? We can also circle back for more at the end of the talk if anything occurs to you. But the research I do now really wouldn't be possible without an incredible group of scientists here at CU. I feel super, super lucky to be working with the whole atomic physics community here, but especially our group. So I work in Jun Ye's group over down the hall at JILA. This whole team of people all work on strontium clocks. So we have 3 different clocks that sit in the same room. So this is the team that I work most closely on here. And each clock usually has 3 or 4 people working on it. And I like to think these are some of the most complicated apparatuses that can test some of the most fundamental physics that you can really build with a team of 3 or 4 people on like an optics table. So I think that's pretty cool. Just to give everybody a roadmap for where we're planning to go today, we'll start first by breaking apart how you can actually use atoms and lasers to tell time. We'll shift over to thinking about why you should care about atomic clocks. What can you actually measure with them? And it turns out there's very practical applications like GPS and very fundamental physics reasons like predictions of general relativity, like gravitational redshifts, which you might have seen in like Interstellar. It's very sci-fi-y, but we can really test this on our optics table. And then we'll back up and talk about what actually makes these optical atomic clocks one of the gold standards for frequency references. So when I say atomic clock, this might sound very sci-fi-y. How do you even use atoms as a clock? But to put this in context, we'll think about what we use to tell time in the world around us. So for example, we might have a pendulum clock like this one. And this has a regular periodic cycle, like pendulum swings back and forth, and you can count the passage of time by counting the ticks of a pendulum. So this is great, but what if we all want to synchronize our concept of time? This is really useful when we're making measurements, we're trying to communicate with other people. The issue with a pendulum clock like this is as it gets warmer or colder or more humid, the wood here could warp or your spring could rust and your clock could start running faster or slower than somebody else's. And that's really inconvenient for a time standard. So you really want some sort of reference so that we all know that we're telling time the same way. So a really ancient way of doing this is using the sun or stars. And so, for example, we could imagine each of us also has a sundial. And so every day at noon, we look up at the sky and we reset our clocks. And so that those 2 ingredients, having a timekeeper, which gives you consistent second by second access to the time, and a reference, which makes sure that we're all counting the same way, are really what goes into what we call a clock. So for us, we actually are going to use atoms to build this reference. So I've shown here the simplest possible atom. This is hydrogen, 1 proton and 1 electron. However, that's where the simple ends. So the world of quantum mechanics kicks in here and really makes us treat this system, which is super microscopic, really differently than the physics that we see in the world around us. And in particular, what quantum mechanics tells us is that certain quantities can only appear in finite chunks or quanta. And so in particular, our electron can only be localized to certain orbits going around the nucleus. So you could find your electron sitting here, or sitting here, or sitting here, but nowhere in between. Now that's like very unintuitive about our world around us. So I'm an experimentalist. I like things that I can see with my hands, so let's do an experiment. So as you guys might be familiar with, if we take any white light source, like a fluorescent light bulb, for example, if we split it up through a prism, we can see that it's really composed of every color of visible light all together. So what's going to happen if we actually use this white light source and we shine it through some sample of hydrogen atoms? Are we going to see the same rainbow as before? Is there going to be an impact on what we can see? Everybody take a couple minutes, say hi to the person next to you, try and meet somebody new if you can, if you came here with friends. And let's brainstorm what you expect to see when we shine a white light source through hydrogen. And if you've seen this before, try and connect it back to this idea of quantized orbits in the atom. Okay, sweet. So conversation sounds like it's starting to die down, so let's all come back together. Did anybody have thoughts about this? I heard the word absorption spectrum floating around a little bit. Did that come up in people's conversations? Yeah, okay. Not that I was eavesdropping or anything, but just standing up there. But in fact, that's exactly what we're going to see. So what we'll see is this the full rainbow, but then bands where that light is gone. It's been taken up by the atoms. Why is this just like chunks of light? Well, each of these orbits of the atom that the electron can occupy actually corresponds to a different energy of the total system. And light also carries energy, which is, you can tell based off of its wavelength. So longer wavelength light, like red light, carries less energy per photon than short wavelength light, like the blue and UV side of the spectrum. And we can really interpret these features in the absorption spectrum and these like very narrow chunks here as corresponding to dynamics happening within the atom itself. This is like, I heard a bunch of people talking about absorption spectrum. So this is something that we as a group have some collective familiarity about, but it's actually kind of cool just how much this like very classically observable thing, shine light, really gives us insight into what's going on a microscopic scale. So you can imagine the atom absorbs a photon of this wavelength and drives one particular transition within the atom, or you can pick up a photon of a different wavelength and drive a different transition. Now, in practice, working in atomic physics, we typically don't draw pictures of these orbitals. Instead, we draw what's called energy level diagrams, which is just a fancy way of conveying the same thing. So each line here is representing one possible state of the atom, and we'll often connect them with lines showing the wavelength of light that addresses them, or some other identifying information. And in atomic physics, when we want to really probe these systems delicately or coherently, where we're talking to just one specific channel here in this atom, instead of using a white light source, we spend a lot of time and effort building optical lasers. So a laser is some light source that you give what's called optical feedback to. So you put it in a cavity or some external reference that amplifies light of a particular wavelength. And so what you get out is a highly coherent beam. It's like one sine wave that's all coming out, and it's at a fixed wavelength. And so when we shine an optical laser on our atom, now we no longer talk to all these other transitions going on. Instead, we're just driving the atom very coherently, very cleanly from one level to another. And you can actually watch the atom oscillate back and forth between these energy levels. Yes.
Could you give an example of a non-optical laser? Like when you say an optical laser, what do you mean by that?
That's an excellent question. So typically when I say optical, I'm talking to something in the visible spectrum of light. So 300 to 700 nanometers-ish. People often will also build microwave clocks, which is a very different frequency band. And you drive these clocks, and sometimes it's not with lasers, but sometimes it's with synthesizers or microwave generators. But you can also build lasers that are either in the extreme like UV or in the extreme IR that wouldn't be in the visible range.
Thanks.
That's an excellent question. Yeah.
Clocks made with like different frequency specifics have like what are the differences between the clocks?
That's an excellent question. It turns out that when you're making a clock, what you really want is the fastest possible reference frequency. So one way of thinking about that is if instead of measuring our like sun once a day, you could measure it, you could get a reference that was like every second, you'd have a much more stable frequency comparison. And so that's why you actually care a lot about the frequency that these clocks operate at, because you want a fast frequency so that you can get the best possible clock. So these optical atomic clocks are really pushing the bounds on new frequency standards, because they operate at hundreds of terahertz that like corresponds to these wavelengths of light, as opposed to previous microwave clocks. So these are really great questions. Yes.
Was it harder, or is it harder to build these higher frequency ones? Like if you're saying that previously they had like a standard that was slower, what are like some of the difficulties that you face or trade-offs between pushing frequency?
That's an excellent question. And it turns out that one of the main technical challenges that's limiting us right now is how well we can build these lasers, these optical lasers. You need a very phase coherent source, and it's very tricky to engineer these. And so our lab works extremely hard on this. And I'll actually chat a little bit more about this later on in the talk. But excellent question. Sweet. And so we've been sort of building towards this, but maybe let's put everything all together. Instead of hydrogen, our lab uses ultra-cold strontium atoms as our frequency reference. So strontium has 2 valence electrons. It's in the second column of the periodic table. And as you include more atomic physics, the energy level diagrams that you have to draw start getting more and more complicated. So I've drawn actually a simplified energy level diagram here, and you can still see there's tons of different transitions that you can talk to in this atom. So you might ask, like, why do we make our lives more complicated by picking an atomic species like this? And it turns out that once you expand to having all of these different transitions to choose from, you can pick some that have like very ideal properties for a clock. And in particular, we pick a clock transition. It's this one right here. It operates at 700 nanometers, 698 nanometers. So that's red. And it's really, really special in atomic physics because if you excite an atom in this state, it'll just sit there for 2 minutes without decaying, without doing anything. And that's really special because 2 minutes doesn't feel like a long time to many of us. But compared to the other states, which can decay in tiny fractions of a second, this is super, super long-lived. And this is really great for a clock, getting back to the question of like why you might pick particular transitions or particular frequencies, because going back to the example of a pendulum clock, you really want a pendulum clock that doesn't damp down. So for example, you can imagine a rusty spring where a pendulum like starts ticking at some frequency and then that motion damps out, as opposed to what you might hear people call a really high Q or high quality factor resonator, where if you start it swinging, it'll just swing forever without damping down. And so that lifetime of the atomic state you can really interpret in the same way. And so our atomic state is super long-lived and coherent. We have a really high Q resonator, no rusty springs here. And in order to really take advantage of this, we have to work very, very hard to engineer very good lasers to interrogate these atoms. But when we do, and we shine this light on this transition, we really see the dynamics I was describing earlier. If we identify the 0 here with the atom being in the ground state and the 1 with the atom being in the excited state, you can really watch the atoms slosh back and forth periodically between these energy levels. And this is exactly the same periodic phenomenon that we were using with our pendulum to tell time. Yes.
Oh, why? Yeah.
That's an excellent question. What you really want is, again, to maximize the what we call the coherence time of these atoms. So how long your sample will remain all ticking at the same rate, for example. And if your atoms are hotter or they're not trapped in a really high vacuum environment, or there's stray magnetic fields going on, anything that could perturb them, the different atoms in your clock will start telling you different times. And so we really try and put our atoms in the most controlled environment possible so that they don't talk to the outside world at all. And so that's an excellent question. When I say ultra cold, really decoupled from everything else going on. Yes.
Is the y-axis the calculation?
Exactly.
So it's like, but why your x is like such a long time?
That's a really, really good question. So this is a very long-lived transition. This is also, this particular graphic is just like a cartoon of this process, but our transition really does live long enough that you can drive this back and forth motion over a second long time scale.
But when you actually drive, you actually use very high frequency drive.
It actually depends on sort of what you're doing. So if you're familiar with different types of spectroscopy, if you're doing something like Ramsey spectroscopy, which involves doing very fast pulses where you're manipulating the state of the atoms by shining like really bright laser light on them for shorter times, yes, we're driving them much more quickly between the different population levels. If you're doing something like Rabi spectroscopy, you can actually use a very, very weak drive. Exactly, very slow. And then you're really talking about seconds long interrogation.
So is this like actual like a scale of your experiment?
So this is not quite what our particular clock does, but other clocks in our lab really do like Rabi spectroscopy with second long pulses. Yeah, absolutely. Yeah.
Just a quick question. What temperature do you classify as a clock?
That's an excellent question. What would you guys call ultra cold in the world around us? Absolute zero. Okay, well, we're not quite that ambitious. Below freezing.
It was 10 degrees the other day. That was pretty bad.
That was so cold. I was not happy about that. Yeah. But for our atoms, we are ultimately able to get them down to hundreds of nanokelvin. So pretty darn cold.
And how do you know that temperature is good enough to have the fluid environment?
That's a fantastic question. So you have to ask sort of, an absolute scale is never obvious when you do this, right? You have to be cold enough compared to what? And in particular, we think about the sort of thermal motion of the atoms compared to the sort of trapping potentials that we set them up in. And so we operate in a regime with our clocks where they're very tightly confined with respect to the sort of thermal kinetic energy that they might have. And in this way, we're able to get very, very narrow atomic line widths. Yeah, these are really great questions, everybody. If there's no more questions at the moment about sort of how atoms can work as a clock, this is the point where I'm going to sort of pivot to why you should care about clocks at all. Because I sort of have just been telling you, oh, clocks are great, but like we all have, yes.
This is supposed to be research that part of my skills. So is that and you make it simple, at least it sounds like it should make that look like a clock. I'm wondering what's the difficulties.
That's an excellent question. So in practice, the actual procedure of trapping these atoms and cooling them down to these 100 nanokelvin temperatures is pretty hard. For my particular apparatus that I work on, we have, I tried to count carefully once, and I think we have like a dozen lasers that we use on our setup, because in the process of cooling the atom down to the level where you can actually talk to it with this clock light, you have to shine light on a bunch of different frequencies and make sure that you're really carefully preparing this ensemble. So that's pretty hard. Building a laser, which before we were talking about building very coherent narrow line width lasers, and we'll get back to that a little bit more later, that's really hard. So all of the technical aspects that go into this is very, very hard, even though I'm describing a very simple atomic physics picture to you so far. Then you open up the next door and you say, okay, well, the atomic physics isn't actually this simple. Our atoms aren't this nice to us. And you can get interactions between different atoms in your sample. You need to very carefully control and account for the densities of the atoms in your clocks. And then you can use them to actually, once you understand and control all of those systematic effects that I've just described, you can now use them to probe fundamental physics. So now, once you have this very well-controlled system, you can use it to test principles like general relativity.
Well, I am. It's great. Part of it just is that as the pattern which is the average that conversation that we inside this, was that given to us, or how was that the original group original work group, was it actually being proven a long time ago that tested was with long time processes?
Sorry, when you talk about that, are you talking about like the energy level diagrams? Or are you talking about the atomic dynamics? That's a good question. Also, these Energy level diagrams are quite complicated. They'll get measured for different species by different groups. I actually don't know who the first group to map out this energy level diagram is, but you have to start measuring these things more and more carefully as you.
Like the theory validation part.
Sorry, what?
The theory validation.
The theory validation part. Yes. So not so much on this side, because now at this point, this part is pretty well understood. But on the atomic physics part, I actually think that, and this is actually what kind of drew me to working in atomic experimental physics. This is really a field where theory and experiment are pushing each other forwards. So I described to you, for example, some of these density-dependent atomic interaction effects. That gets pretty complicated really, really fast when you can measure with the precision that we can on these clocks. And so this was a real example where one of our apparatuses was seeing something that they didn't quite understand with their density shift data. And they took it to Anna Maria Ray, who's a theorist in JILA, and they said, hey, we're seeing this really weird thing, like, what's going on? And there were like countless hours spent brainstorming together, working through the math together, experiments and theory going back and forth and doing more tests. And in the end, they were able to build out new models for what microscopic atomic physics in terms of interactions were taking place. And so I think that's super, super cool. So, and that's theory on the side of like atomic physics. But as we'll see in just a minute, once you actually build these clocks, you can use them to test fundamental physics across a variety of different fields. And we'll break down gravitational redshifts up next. That's a great question. Any other questions about this section? Sweet. So we're going to get into why clocks are good. And in general, this is just because precision measurements of time let us determine a whole bunch of quantities that we really, really care about. So for example, GPS, or how we tell where we are on the world, fundamentally operates based off of time intervals, and how precisely you can measure the passage of time sets how well you can tell where you are in space. So for the way this works is your watch or phone or whatever is GPS enabled these days pings out signals to many different satellites and records how long it takes to hear back from those satellites. So because we know very well the speed at which light travels, we can turn that into how far away we are from multiple satellites, and from that you can triangulate your position. So I can say, I know I'm 30 feet away from those chalkboards, and I'm 5 feet away from the window, and I'm 40 feet away from those shelves over there. And based on that, you can sort of draw out the geometry and figure out exactly where in the room I must be standing. So if you care about practical things like being able to like do better localization of like where you are with GPS, you should care about clocks. But if you also care about testing fundamental physics, you should also care about clocks. And so I'm going to tell you some of the background of a paper that some of my lab mates put out quite recently, where we were able to measure predictions from general relativity in our lab sitting on a table. So general relativity is Einstein's theory of gravity. And it has one prediction in particular, which is called a gravitational redshift. So have people seen Interstellar? Okay, yeah. So this might be a spoiler, but you know the part where like the guy falls into the black hole, and then because of the crazy gravity, now he's like younger than his daughter. So that's actually based off of a very real physical phenomenon, which is the fact that time ticks slower for an observer that's seated in a deeper gravity well. And so we can set this up instead of, in black holes and sci-fi, really in a real world example, if you compare somebody who's sitting on the surface of the Earth to an astronaut floating up by the International Space Station, which is about 400 kilometers above the Earth. And this prediction of GR is that the astronaut's watch will be ticking faster than ours on the ground. So, there's theorists who do this very, very carefully and can tell you exactly the prediction that GR would give. But what I think is pretty cool is you can build intuition for this answer using something called dimensional analysis, which you guys might have seen in physics classes, where you can take, some intuition about how your system works and some physical constants that you think should matter, and you mash them together until you get a number out. And that number tells you something about your system. And you can actually use this to predict exactly how large this effect should be. So first off, we're going to brainstorm. So turn to your partner. This is going to be a quick one. So 30 seconds a minute. What physical constants seem relevant to the system? Okay, amazing. So we're going to keep thinking through this problem in just a minute, but I want to sort of crowdsource this part first. So what constants do people come up with? Speed of light, excellent. G, excellent. Which G in particular? Sweet. Any other G like things that might factor in there? Any other constants in general? Mass of the Earth, sweet. Yeah, that definitely seems relevant if we're talking about the gravity from Earth.
Is mass of Earth like a constant?
It probably is something that's important for setting the scale of this effect. Yeah.
So the diameter.
Yeah, the radius. Yeah. Yeah, exactly. And then we're going to add in just like a smidge. I really like all of these things that we're throwing out here. And in fact, a lot of these are exactly what I'd written down when I sat down to like try and convince myself of this as I was writing my talk. And I was like, oh, it's cool that you can just estimate this. And like these things that you're throwing out are exactly the same things that I jotted down here. One piece of intuition we can use to guide ourselves is the typical form of a gravitational potential or gravitational field. And so we know this is like a 1/r potential. So that's why the astronaut feels a weaker gravitational field than a person back on Earth. So now that we've sort of got a shared collection of constants, go back to your groups and see if you can come up with a way to smash these all together to get something that is dimensionless. So no units. And what that's going to represent is the ratio of how fast this clock ticks with respect to that one. So I'm hearing some really great ideas here. I want to try and like put them together because it sounds like lots of people have good thoughts on this. Can anybody tell me a little bit about your thought process for this?
I mean, we were just thinking that we can find a potential, gravitational potential at Earth and at further distance. And since like the change in the time is one of the big factors, the gravitational force, then that potential can tell us how the gravitational force is changing the distance.
I love that. In fact, that's how I was thinking about this problem as well. Does anybody have an idea for how we can make that simpler for ourselves though, right? Because this is kind of a complicated analytical expression. I'm looking for something very, very simple.
Okay. Like the ratio, the range depends on the ratio of radius.
Because others are constant.
Yeah, so that's a really great idea or intuition from that, and you can actually get that exactly from the form of the potential. I'd kind of like called this R and delta R, and you'll notice that like delta R is much smaller than R. Does this like sound like a familiar setup to anybody? Are there any techniques you can use to make things simpler when you have a limit like that, where you have one quantity that's smaller than another? Taylor expansion, yes. Okay, excellent. Everything in physics is dimensional analysis and Taylor expansion, guys. Did anybody else have thoughts about how you were addressing this problem? I think there's lots of different ways you can break the system apart and get it to make sense. Yeah, Tyler.
It seems you do R times G divided by C squared, that cancels out all the units, I think.
Yeah. I think there might be an extra factor of mass lurking around in there. If you're thinking about big G.
It's a little.
Perfect. No, perfect. No, you did it. So that definitely has the right units. And then the question is, does that match our physical intuition for the system? And like you can like brainstorm and like think about this, but it is a little bit tricky because unfortunately, like there's two different length scales here that have the same units. There's the radius of the Earth and then there's a radius in between. And this is where dimensional analysis can get a little bit tricky. And we're going to have to like take some limits and do some Taylor expansions to really figure out what quantities we need to plug in there. But that's a great observation. And in fact, that's exactly the sort of logic that goes in here. So we take this difference exactly as this group over here had suggested. And when you do the Taylor expansion of this, you find that it looks like GM over the radius of the Earth squared times this little distance, delta R, to first order. We don't care about higher order. And we recognize that this quantity is exactly little g, as like Tyler had also like picked up. That has great units for our problem. And this kind of makes sense because we're sort of imagining we have like a test mass at both of these locations. And we're thinking about the impact of gravity at those points. And so once we do this, we see that we have a quantity that has units of meters squared per second squared. And we can slap on a factor of c squared to get a dimensionless quantity. Great, we went through all this work. I made you guys do math. Why do we care? Well, this actually lets us estimate directly the magnitude of this effect from GR. And so it turns out that if you apply this to the situation of the International Space Station, you'd find that an astronaut up at the space station would age more quickly by a rate of 0.5 millisecond per 6 months. That's a tiny effect. And to put that in scale, that's a 10 to the minus 10 level difference between the rate of the person on Earth and the person on the satellite. And in practice, if you guys go and like look this up, there's other time dilation effects that also play a role. So I heard some people brainstorming what sounded like special relativistic effects, and those are much larger in this case. But this is a very real effect, and it's been measured many, many times over. So this started in the 70s, where people sent clocks up in airplanes and had them go around the world, and then see how that time had elapsed compared to clocks that stayed put. And then people started sending clocks up to high floors of skyscrapers, and you could measure that effect now on smaller length scales. Yeah.
Do you know when, like, the first pass on the difference, like if this was predicted in like I guess early 1900s?
Yeah, and that first, the first one that I'm aware of in terms of like the airplanes, was I think 71, like early 70s. I don't know if you can possibly observe this through other like astrophysical phenomenon. Every time we think we've done something really clever, there's an astrophysicist who's like, actually, we measured this on a galactic scale 5 years ago. So maybe somebody else had done this a different way first. But yeah.
What the accuracy of the top?
That's an excellent question. I'm actually not totally sure. Amazing questions here. But we went from airplanes to skyscrapers to a few years ago, people had done this on like a meter length scale. And our lab has now been able to do it on a table. In fact, a 1 millimeter length scale. And so the way that this works is we've talked about our atoms are ticking at some standard frequency. We form a cloud of these atoms through some of the trapping procedures we were talking about before. And this cloud is about 1 millimeter in length. So our optical table is sitting down here. And so these atoms are slightly closer to the floor than these atoms. And so if we take that expression from the last slide and we plug in a 1 millimeter length scale, we now find that there's a 10 to the minus 19 level effect between these clouds, top versus bottom. And my lab mates measured this. That's crazy to me. Yes.
You're saying the absorption spectrum line, it shifts with altitude?
It does, yes, exactly. The frequency that these clocks will reference, exactly. This is not something that you can see on any one individual shot of an experiment, but they were able to build this incredibly stable clock and average down for a weeks-long campaign in order to measure this number. And 10 to the minus 19 sounds so far removed from our like daily experience that it's sort of hard to put that number in context. It's been about 10 to the 19 seconds since the Big Bang. So a similar level of precision measurement would be if you were able to tell me the age of the universe up to 1 second in precision. And like, that's wild to me.
How did you guys do that?
How did we do that? Wow, you're leading me into my talk. So perhaps it's intuitive that to make a really, really good measurement, you need a very, very good clock. And so if you have a better clock, you can average down to make a measurement of a certain precision faster. The metric that quantifies this is the clock stability. And the thing that I was just describing is the fact that this scales, this depends on the total elapsed time, in particular, like 1 over the square root of the elapsed time. And so what you really, really want is a good clock stability, everything else in this expression, so that you can make a measurement of a given precision without having to wait too long. And the sort of confusing thing maybe about stability is low stability is actually good. Means you can measure better. All the factors are on the denominator here. We sometimes jokingly call it the instability of our clocks, but we just like to be confusing like that. But what's actually kind of fun is I put this up here because just to answer your question, you can actually understand where these factors for this clock come from and why the clocks we build are really, really good at it. So for one, as we were talking about earlier, is the reference frequency that our clocks operate at. As we were saying before, higher frequency is good because you get to accrue more signal as you're measuring. You get to fine tune your clock more often. And so our clocks operate at hundreds of terahertz, optical clocks. And this is really the state of the art in terms of optimizing this figure. Then what you really want to do is it takes some amount of time for us to prepare our atoms. I talked about needing to cool them, needing to trap them. This takes like seconds. So once we set them all up, we really want to interrogate them with our clock laser for as long as possible before we have to throw them away. And the longer you interrogate them for, the more signal you get before you have to go through this whole phase of loading your clock again. So what you really want is for the single cycle interrogation time, that's what that means, how long we get to talk to our cloud of atoms, to be as long as possible. And this is limited by the coherence time of either your atoms or your laser. So I told you before that our atoms live like forever. They live like 2 minutes. We're great. Because we go to all the trouble of cooling and trapping them like this, which is actually, I shouldn't gloss over that because that's a lot of really hard work. But our laser, it actually turns out to be a real feat of engineering to get it to live this long. And it might be confusing to think about a laser being noisy, but you can really think about what we want is for our laser to be outputting a solid sine wave that's coherent. And one of the limiting sources of noise for us is what we call phase noise. So if the phase of your sine wave is slipping with respect to the phase of some reference wave, that is a contributing noise source. And once you get to the point where your wave is slipping around like this, you have to reset your clock and start your measurements again. And so using like state-of-the-art engineering, referencing lasers to cryogenic cavities, again, to get the most controlled possible environment, we've been able to extend these lifetimes out to order seconds, now approaching 10 seconds. So we're really pushing that engineering. And Jun's lab really specializes in this, and he's been pushing at the forefront of ultra-stable lasers for the last, I don't know, decades. And then finally, here's something actually related to the atoms, which is I kind of snuck a fast one past you guys earlier when I said that we could watch the atoms ticking back and forth between the two states the same way you could a pendulum clock. Because anytime you measure an atom, you're always going to find it in one of the eigenstates of its system. It's either going to be in 0 or in 1. I can never look at one single atom that's if we're here on this time curve, I can never look at one single atom and have it tell me I'm 25% in the excited state. That's not allowed. If you were to perform that measurement many, many times over, you'd see it manifest because 75% of the time you'd measure the ground state and 25% of the time you'd measure the excited state. So what do? We build up statistics, and we do this by trapping and interrogating many, many, many atoms. Because it turns out if you think about what this looks like, if you're sitting right halfway in between the states, each atom has to pick, am I up or am I down? Binary choice. And those statistics end up looking exactly like the classical noise associated with flipping coins. And so if you exactly wanted to measure, a 50% chance of flipping coins, and you wanted to make the noise on that as small as possible, the law of large numbers tells us that you can get closer to the expected value, like 1 over square root of the number of coins you flip. And this is sort of what you get for free with your atomic sample. But we are now really trying to push every single factor to make these clocks better. And so the particular experiment that I work on is trying to leverage a truly quantum property, which is entanglement, to make these clocks run better. And the way this sort of works is if we imagine we take atoms that are sitting at the halfway point here and we measure them, we'll get some noise associated with the outcome. So what I'm showing here is the spin observable. So up or down is what's labeling this axis. And we're measuring this for like 10,000 atoms. So this axis really scales from like minus 10,000 to plus 10,000. And the noise on this measurement is really associated with the projection noise of these atomic ensembles. But once you make this measurement, you can make it again. And each one looks individually really noisy, but you'll find that their difference is really, really small. And we can actually understand this by appealing to the property of entanglement in quantum mechanics. So the act of measuring our atomic system here really fundamentally has changed what our sample looks like afterwards. After we perform this pre-measurement, this is what this P stands for here, we've actually changed the spin distribution of our atoms so that we can now think about this as being smaller in the observable associated with what we want to measure. So I said Z is what we're measuring. This figure right here is called a Bloch sphere, which represents the sort of spin observables of an atom. So you can think about up here, North Pole being measuring 1 on this graph, and down is 0. But there's other non-commuting observables that dictate the spin of a sample. For example, in this case, the X, Y factors. And it turns out that since these observables don't commute, you can apply the same Heisenberg principle type of thinking to think about what happens to the total state uncertainty. So once we measure very precisely on this axis, just as we make the argument that you can't know both the position and momentum of an atom very, very well, we've now localized our state along this axis, and it's really fuzzy along this one. Turns out that's fine for clocks because we only need to measure this way. And so in this way, we can prepare entangled samples and actually use this to reduce the projection noise associated with that clock operation that I was telling you about. And what this typically is expressed at is some sort of gain factor from spin squeezing. And it's really, really hard to build this into clocks without decohering them. But in our recent paper, which I've put down right here, we were actually able to get our clocks to average down a factor of like 1.5 times faster. So this number here could be like a 0.67. And when you put all of these things together, this is how we do it. This is how we make these measurements. So we work at optical frequencies. We work with seconds long interrogation times. We pack as many atoms as we possibly can in 10,000 to 100,000 atoms for each clock. And we're working on like the cutting edge of adding spin squeezing to these atomic clocks to get every possible win so that we can get a 10 to the minus 17 per root tau fractional frequency stability. You can sort of see this. This is actual data now from a paper from Sarah Campbell, a recent graduate from our group, where you're measuring the frequency response of the atoms. And you can see that the atoms are able to tell you about changes on the order of a hertz out of a 429 terahertz transition. And that's like a way to really visualize what this 10 to the minus 19 stability looks like. And so the lower your stability, the better that number gets, the less time you have to spend averaging to make a precision measurement at the 10 to the 19 level. I've thrown a lot of atomic physics, quantum physics, entanglement, general relativity at you guys all in 1 hour. Does anybody have questions? Yes.
So you're talking about these oscillating waves at terahertz frequencies. Are you looking for like, you like count the peaks in that wave?
Okay, so that's an excellent question. So what you end up doing is scanning out a frequency response like this to your atoms. So you vary the frequency that you're shining on them, and you look at how many atoms are in the excited versus ground state. So, and then you sit somewhere where you have a linear slope. So you sit like close to the 50-50 point here for your set point.
Okay.
And then you wait and you run the experiment over and over and over. And sometimes you measure 51% and sometimes you measure 49%. And when you make that measurement, you use that to steer back and correct your laser frequency. So it's tracking your atomic ensemble through time. So that's an excellent question. Our reference frequencies are terahertz. That's like how quickly we're accumulating this signal. But we actually only perform this readout every, few seconds. Was there another question over here? Same question. It was an excellent question, actually. So we are about to wrap up here pretty soon, but maybe I'll just talk about what it actually is like working on one of these setups. I think it's so fun being an experimentalist, especially getting to build up a new apparatus, because you really get to get your hands dirty on every single part of this machine. So when I joined, I'm a third-year graduate student now. So I joined this project 2.5 years ago, and it was a new project. People had spent years brainstorming and deciding what we were going to do and what we were going to build, but it hadn't actually been assembled yet. So I came and our optical table was just empty. Crazy. We worked really, really hard for 3 months assembling a vacuum chamber. So I've been telling you about how we need to get these atoms away from the outside world. And so we keep them in ultra high vacuum environments. So this was it's kind of wild doing UHV work if people have done it. You're wearing gloves, you're in a bubble to keep dust from getting in. It feels like precision surgery or something. Not that I have experience with that, but and then things dramatically changed, because now it was time to start doing the optics, building all those laser systems. I told you guys we have about 12 lasers. So we had to build all that. And then we finally got to spend some time doing what you typically think of as a physics PhD. We were taking data to understand our system and eventually fixing things. And at the end of this, we wrote a paper and submitted it. And so we're doing data analysis on our system. So the sort of day-to-day things that you might think a physics PhD is. And then you go back and you do it again. So once we got this result out, we started doing a new round of experimental upgrades to really identify the factors in our experiment that we could improve to make even cooler results next time. So I've been doing a lot of very finicky optic setups, just making sure that some of the beams that we really, really care about are gorgeous and Gaussian and very pretty. So it really looks very, very different every day in lab. And I love that about experimental physics. So that's all I have planned today. I'm super happy to take questions if people have any others.
Excellent. Great. Well, thanks everyone for coming out. If you have a minute to fill out this quick survey, there's a QR code and a link there to let us know how we can make these talks better. And if you'd like to help out with the C Prime Talks team, we're always happy to get more people on board with helping with the setup or any other aspect of it. So feel free to talk to me afterwards or send an email to cprime talks@cprime.org. We have maybe a minute or two for some questions, if anybody has any more for Maya.
You're also welcome to come up after if you want to chat about any part of this. Yeah.
What's the next goal for the lab?
What's the next goal for the lab? Each of our different clocks, I showed you this whole team of 15 people is pushing different directions. For my particular project, the result that we just put out, which we're really excited about, was showing that we can actually make clocks tick below a fundamental limit that you can see with unentangled samples by adding the spin squeezing in. And we really want to push that. We want to take that factor of 1.5 that we won and really make that even bigger. Thanks.
Yeah, but with some of the applications that was
Yeah, for the fundamental physics direction of this.
yeah, for applications.
Sure. So as fundamentally, the way that we think about quantum mechanics and gravity is pretty tricky. And so it's actually quite cool to be able to measure these general relativistic effects on smaller and smaller and smaller length scales. So 1 millimeter is pretty good, but we're already sitting down and thinking about theory proposals to, can we think about measuring this effect over the size of one atom's wave function? And can we really look at it coherently as atoms like tunnel around in our lattices? And this is where you really have to move beyond this like linear single particle picture of quantum gravity and start to think about how all of these effects go together. So we're working with some of our theory collaborators, fleshing out those ideas. You can also probe questions about dark matter, for example, by looking at how the fundamental physics that constants that go into setting the transition frequencies for these different clocks should oscillate in time if you imagine that you use like very light sources of dark matter. And you can use this to put bounds on different dark matter candidate ideas based off of the fact that we don't measure those fluctuations.
Okay, so well, if anyone else has any more questions, feel free to come up, talk afterwards. But if not, let's thank Maya one more time.